Hey future chemists! Welcome to our one-shot on chemical kinetics, the study of how fast reactions happen and what controls their speed. In the next 20 minutes, we are going to master everything. We will cover rate laws, reaction order, molecularity, the integrated rate equations, half-life, the Arrhenius equation, collision theory, and finally, catalysis. Plus, we will solve 3 important numericals to really lock in your concepts. This unit is a favorite in NEB exams, so let's make it our strength. Let us go. Hello students. Today, we're diving into chemical kinetics, the study of reaction speed. So, what is the rate of reaction? It's simply the change in the concentration of any reactant or product over a specific period of time. We can calculate the average rate, which is the total change in concentration divided by the total change in time. We use a negative sign for reactants, as they are consumed, and a positive sign for products. For a more precise value, we look at the instantaneous rate, which is the rate at a specific moment. This is the limit as delta t approaches 0, or simply dc by dt. The most common unit for reaction rate is moles per liter per second. For a general reaction, let's say AA plus BB gives CC plus DD, the rate is -1 over A times dA by dt, which equals -1 over B times dB by dt, and so on for the products, ensuring we have a single positive value for the overall reaction rate. So, how do we mathematically connect reaction rate with reactant concentrations? We use what's called the rate law, or the rate equation. A rate law is an expression that is found through experiments. It is not theoretical. For a general reaction where A plus B gives some products, the rate law would typically be rate equals K times the concentration of A raised to the power m times the concentration of B raised to the power n. In this equation, K is called the rate constant. Its value depends on the reaction and the temperature. The exponents, m and n, are the reaction orders. We say the reaction is m order with respect to A and n order with respect to B. A key point to remember is that the rate law is determined experimentally. We cannot just look at the stoichiometric coefficients of the balanced equation to figure it out. Let's clarify 2 key terms, order and molecularity. The order of a reaction is an experimental value. It's the sum of the exponents in the rate law, for example, m plus n. This value can be an integer like 0, 1, or 2, and it can even be a fraction. Molecularity, however, is a theoretical concept. It refers to the number of reactant species that collide in a single, elementary reaction step. Since it represents an actual collision, molecularity must be a positive integer, typically 1 or 2. Here's the main distinction: for a simple, single-step reaction, the order will equal the molecularity. For complex, multi-step reactions, the overall order is governed by the slowest step, which we call the rate-determining step. A special case is a pseudo-first-order reaction, where a second-order reaction behaves as first-order because one reactant is in huge excess. Finally, what factors can change the rate of a reaction? First, the concentration of reactants. Higher concentration leads to more frequent collisions, which generally increases the reaction rate. Second is temperature. Raising the temperature increases the kinetic energy of molecules, causing more frequent and more energetic collisions. As a rule of thumb, the rate often doubles for every 10 degrees Celsius increase. This is known as the temperature coefficient. Third is the presence of a catalyst. A catalyst provides a different reaction pathway that has a lower activation energy, speeding up the reaction without being consumed. Fourth, for reactions involving different phases, is surface area. Grinding a solid into a powder increases its surface area and thus the reaction rate. Fifth is the chemical nature of the reactants themselves. And finally, some photochemical reactions are initiated by exposure to light or other radiation. Let's begin with zero-order reactions. In these reactions, the rate is completely independent of the reactant concentration. This means the reaction proceeds at a constant speed, regardless of how much reactant is left. The rate law is simply rate equals K, where K is the rate constant. The differential form is minus dA by dt equals K. If we integrate this equation, we get the integrated rate law, A equals A naught minus KT. This is the equation of a straight line, y equals mx plus c. So, a plot of concentration versus time gives a straight line with a negative slope equal to minus k. Now for the half-life, which we call t-half. This is the time it takes for half of the reactant to be consumed. Setting it equal to a naught divided by 2, we find that t-half equals a naught divided by 2k. Notice here that the half-life depends on the initial concentration. Common examples include some photochemical reactions and enzyme-catalyzed reactions when the substrate concentration is very high. Next, we have first-order reactions, which are very common in chemistry. Here, the rate is directly proportional to the concentration of a single reactant. The rate law is written as rate equals k times the concentration of A. This means the differential rate equation is minus dA by dt equals k times A. To get the integrated form, we separate the variables, putting concentration terms on one side and time on the other. This gives dA divided by A equals minus k dt. Integrating this from time 0 to a time t, we get the natural log of A divided by a naught equals minus kt. For practical calculations, we often use the base 10 log form. The equation becomes k equals 2.303 divided by t times the log of a naught divided by A. Now, let's find the half-life. We set time t equal to t-half, and the concentration A becomes a naught divided by 2. Substituting this into our natural log equation, we find that t-half equals 0.693 divided by k. This is a crucial result. The half-life of a first-order reaction is independent of the initial concentration. It's a constant value, a key characteristic used to identify these reactions, such as in radioactive decay. Now, let's explore how temperature affects reaction rates using the Arrhenius equation. This equation provides a quantitative relationship between the rate constant, K, and temperature. It is given as K equals A times e to the power of minus EA divided by RT. Let's break this down. A is the pre-exponential factor, or frequency factor, which relates to the frequency of collisions. EA is the activation energy, the minimum energy required for a reaction to occur. R is the universal gas constant, and T is the absolute temperature in Kelvin. To make this equation more useful for experimental analysis, we can take the natural log of both sides. This gives us natural log of K equals the natural log of a minus EA divided by RT. This equation is in the linear form y equals c plus mx. By plotting the natural log of K on the y-axis versus 1 divided by t on the x-axis, we obtain a straight line. The slope of this line is equal to minus EA divided by R. This graphical method allows us to determine the activation energy of a reaction from experimental data. Finally, let's look at the microscopic level with the collision theory of reaction rates. This theory states that for a chemical reaction to happen, the reactant molecules must first collide with each other. However, not every collision results in a reaction. For a collision to be effective, two key conditions must be met. First, the colliding molecules must possess sufficient kinetic energy to overcome a barrier known as the activation energy, EA. This is the minimum energy required to break old bonds and form new ones. Second, the molecules must be in a proper orientation at the moment of impact. If they are not aligned correctly, they will simply bounce off each other, even if they have enough energy. Therefore, the rate of a reaction is proportional to the collision frequency, which is the total number of collisions per unit time, multiplied by the fraction of those collisions that are effective. This orientation requirement is accounted for by the steric factor, P, which is a component of the pre-exponential factor, A, in the Arrhenius equation. Hello students, let's solve a problem from chemical kinetics. The question is, a first-order reaction has rate constant K equals 2.303 times 10 to the minus 3 per second. Calculate its half-life. Okay, let's start by listing what we know. The problem tells us two key things. First, it's a first-order reaction. Second, the rate constant, K, is 2.303 times 10 to the minus 3 per second. Our goal is to calculate the half-life, or t-half. For a first-order reaction, the relationship between half-life and the rate constant is given by a specific formula, T half equals 0.73 divided by K. This is a very important formula to remember. Now, we just substitute the value of K into our equation. So, T half equals 0.693 divided by 2.303 times 10 to the minus 3. Let's do the calculation. The denominator is 0.002303. So we have 0.693 divided by that value. This calculation gives us approximately 301. The unit for K was per second, so our half-life will be in seconds. So the half-life is 301 seconds, which is about 5 minutes. And that is our final answer. Simple, right? Now let's explore a fascinating concept called pseudo-first-order reactions. These are reactions that are truly second-order by nature, but they behave as if they are first-order under specific conditions. A classic example is the hydrolysis of an ester, like ethyl acetate, in a large amount of water. The overall reaction is CH3CuC2H5 plus H2O gives CH3Cu plus C2H5OH. The true rate law would be, rate equals K times the concentration of ester times the concentration of water. However, since the reaction occurs in an aqueous solution, water is the solvent and is present in such a huge excess that its concentration remains virtually constant throughout the reaction. We can therefore combine the constant K and the constant concentration of H2O into a new constant, which we'll call K prime. The rate law simplifies to rate equals K prime times the concentration of ester. It now appears to be first order, hence the name pseudo-first order. A catalyst is a substance that increases the rate of a chemical reaction without being consumed itself. It does this because it provides an alternative pathway with a lower activation energy. We can classify catalysis into several types. First, homogeneous catalysis, where the catalyst and reactants are in the same phase, like the acid-catalyzed hydrolysis of esters using aqueous H2SO4. Second is heterogeneous catalysis, where the catalyst and reactants are in different phases. The famous Haber process, where nitrogen and hydrogen gas react on a solid iron catalyst, is a prime example. Third, we have autocatalysis, where a product of the reaction itself acts as a catalyst. The reaction between potassium permanganate and oxalic acid is a classic demonstration. Finally, enzyme catalysis involves biological catalysts, which are highly specific proteins. For instance, the enzyme amylase in our saliva breaks down starch into sugars. We know that increasing temperature increases reaction rate, but by how much? For many reactions, a 10 degrees Celsius rise in temperature roughly doubles or triples the reaction rate. This relationship is described by the temperature coefficient, which is defined as the ratio of the rate constant at temperature T plus 10 to the rate constant at T. A more precise quantitative relationship comes from the Arrhenius equation. By measuring the rate constants at two different temperatures, T1 and T2, we can use an integrated form of this equation. It states that log of K2 divided by K1 equals the activation energy, E sub A, divided by 2.303 times R, all multiplied by T2 minus T1, divided by T1 times T2. This powerful equation allows us to experimentally determine the activation energy for a reaction. To understand how reactions happen on a molecular level, we use what's called the transition state theory. It proposes that as reactant molecules approach each other and collide, they form a high-energy, unstable intermediate arrangement called the activated complex or transition state. This complex is at the very peak of the energy profile diagram. The minimum energy required to form this activated complex from the reactants is the activation energy, E sub A. Think of it as an energy barrier that must be overcome. A catalyst works by providing a different reaction pathway with a different, lower energy transition state. This is why a catalyst lowers this barrier. Finally, the overall enthalpy change, delta H of the reaction, can be found by subtracting the activation energy of the reverse reaction from the activation energy of the forward reaction. Hello students! Let's solve our first numerical on chemical kinetics. The question is, for the reaction A plus B gives products, the rate doubles when the concentration of A is doubled. And, when the concentration of B is doubled, the rate quadruples. We need to find the rate law and the overall order of the reaction. Let's break this down. First, when A is doubled, the rate also doubles. This shows a direct, linear relationship. So, the order with respect to A is 1. Next, when B is doubled, the rate quadruples. Now, think about what 4 is. 4 is 2 squared. This means the rate is proportional to the square of the concentration of B, so the order with respect to B must be 2. Now we can write our rate law is rate equals K times concentration of A to the power 1 times concentration of B to the power 2. Finally, the overall order is the sum of the individual orders, 1 plus 2, giving us 3. So the reaction is third order overall. Let's move on to our second problem. Here, the rate constant of a reaction doubles when the temperature increases from 300 Kelvin to 310 Kelvin. We need to calculate the activation energy, E. We are given R equals 8.314 joule per mole Kelvin, and the natural log of 2 is 0.693. For this, we must use the Arrhenius equation in its two-temperature form. The formula is natural log of K2 by K1 equals E divided by R times 1 by T1 minus 1 by T2. Since the rate constant doubles, the ratio K2 by K1 is 2. Our temperatures T1 and T2 are 300 and 310 Kelvin, respectively. Substituting the values, we get natural log of 2 equals E divided by 8.314 times 1 by 300 minus 1 by 310. The term in the bracket simplifies to 10 divided by 93,000. So, 0.693 equals E over 8.315 times 10 over 93,000. Rearranging the equation to solve for E gives us E equals 0.693 times 8.314 times 9,300. This calculates to approximately 53.70 joules per mole, or more simply, 53.6 kilojoules per mole. All right, students, a quick recap of chemical kinetics. Remember these key points. First, the rate law, rate equals K times concentration of A to the power X times concentration of B to the power Y. For your NEB exam, the absolute must-know formula is for a first-order reaction, K equals 2.303 divided by T times log of a naught over A. This directly leads to the half-life for first-order reactions, T half equals 0.693 divided by K. Also, remember the Arrhenius equation, natural log of K equals natural log of a minus EA divided by RT. And finally, what does a catalyst do? It simply lowers the activation energy, EA, to speed up the reaction. Now for some crucial exam tips. The most common trap question in NEB involves the units of the rate constant, K. Remember, they are different for 0, first, and second order. You must memorize the first-order formulas we just discussed. Numerical problems based on them are almost guaranteed. A time-saving trick, know the Arrhenius plot. If you're asked to find activation energy from a graph of natural log of K versus 1 by T, remember that the slope of that line equals minus EA divided by R. This question style has been asked year after year. Stay calm, focus on these key areas, and you will do great. You've got this. And that's a wrap on chemical kinetics. Congratulations on making it through. Remember, the most important formula is the first-order integrated rate law, K equals 2.303 divided by T times log of A over A minus X. If this video helped you, please subscribe and like. Drop a comment below with which chapter you'd like to see next. Coming up, we'll be tackling Unit 4 thermodynamics. Stay tuned for that.